Okay, so let's say you have a curve like y equals x squared, and you want to find the area under the curve from 0 to 1. So thinking about how to do this, you could try approximating it by drawing some rectangles because it's really easy to find the area of a rectangle. It's just the base times the height. So you can draw a few rectangles under the curve, and it looks like this. And it's easy to find the area of those rectangles because the base is just um, the x distance, which is 1, over the number of rectangles there are, which is 4, times the height, which is just the value of the function at the point. So here it's 0, here the height is 1/4 squared, so it's 1/16. Here it's 2/4 squared, so it's 1/4, and so on. And the area of the rectangle is that base times the height. And so you can just sum up the area of these rectangles and get an approximation for the area under this curve. But it's not a very close approximation right now because, as you can see, it's an underestimate because these rectangles do not fill up all the area under the curve. There's this empty space. They don't go above the curve at all, but they're below the curve, and they don't fill up all the area below the curve because there's the area not covered by rectangles. And so the actual area under this curve, x squared from 0 to 1, is 1/3. But these rectangles only have like 0.22 area covered. So they only have like maybe 2/3 of the area covered. There's still this part that's not covered by the rectangles. And so we can get closer to the actual value simply by just drawing more rectangles. So if we draw a bunch more rectangles, you can see that the area not covered by rectangles under the curves is getting smaller. And so with like 20 rectangles, you can see that most of the area under the curve is covered by rectangles. It's still an underestimate. It's still not quite the actual area, but it's approaching the actual area as we increase the number of rectangles. Now it's like 0.31, so it's pretty close. It's getting there. And so we say, well, all right, as the number of rectangles approaches infinity, the rectangles start getting really thin. They just become lines, and there become a lot of them, like an infinite amount of them. And so we draw more and more rectangles, and the area not taken up by the rectangles become smaller and smaller, and it gets closer and closer to the actual value. And so with like 100 rectangles, we're at 0.328. So not, it's still a finite number of rectangles here, and it's not quite close. But we could, instead of doing it like this, we could turn it into a limit because that's what it is. It's as the number of rectangles approaches infinity, they become, thin like lines, but there's an infinite number of them. And in this case, when you evaluate the limit, it's something like, I think 2x squared over 6x squared or something. It's how it ends up. So as x approaches infinity, it becomes 1/3, which is the correct area under this curve. Um, and that technique of saying, okay, well, as we have approaching an infinite number of rectangles that are just lines under this curve, we'll be able to exactly get the area because the area will approach the actual area, or rather the area approximated by the rectangles will approach the actual area. Because as you can see now, there's very little area under this curve not covered by rectangles. And as the rectangles approach lines, they'll cover all the area. And so that's pretty much what a Riemann sum is. We're summing up a bunch of rectangles as it approaches an infinite number of lines to find the area under the curve.